Okay. Okay. Let's quickly go over these guidelines, okay, so that we can move on to the next chapter, okay. Okay, the first one is number of hidden layers. Okay, so you know, basically you should start with like a small number of hidden layers, but in terms of parameter efficiency, okay, sometimes if you feel like okay, the model is not complicated enough, I want to either add more number of neurons or add more layers, okay? If you have these two options, okay, then, okay, adding more number of layers normally will give you better parameter efficiency, okay? So, so shallow model normally has a much worse performance than the deeper one, especially, it doesn't matter like how many neurons you have at each layer, okay? And later on when we talk about CNN, you will see like we actually, especially like at first like stage of the CNN development, you can see the model become deeper and deeper, okay? This actually echoes this parameter efficiency argument. Okay, the deeper model has a better parameter efficiency than the shallow model. Okay, just want you to understand this. Okay, so one way to explain why this is the case is that, okay, for example, say if you want to draw a forest, okay, using some drawing software, okay, but you are forbidden to copy and paste anything, okay, it will take an enormous amount of time, right? So basically, you just like have to draw everything like one stroke at a time, okay. But if you are allowed to do copy and paste, for example, then you can draw one leaf, and then you can copy many leaves to become a tree, right? And you can copy many trees to form a forest, right? So by doing this simple copy and paste, it allows you to finish the drawing of a forest in a much more efficient manner, right? So having like more layers is something like that, because the lower layer take care what should I say, like the more simple features, and the higher layer can focus on more complicated, more advanced features. For example, the lower layers normally can detect maybe like the orientation of a line, something like that. And the higher layer can detect maybe the shape, maybe like it's a rectangle, it's a circle, it's an oval, in a higher layer. So it actually, having multiple layers allow the model to divide the task into like a simple ones and a complicated one. I mean, by doing that, I mean, it will actually give you a much, more efficient model. Okay, something similar to like using copy and paste to draw a forest. Okay, so this is like just want to give you an idea. Okay, and once you understand this thing, okay, so the model, as I said, like the lower layer deal with like a more simple feature, the higher layer deal with more complicated feature, then you can immediately understand the concept of transfer learning. What the transfer learning is, okay, is you try to use a model that is doing a similar job for another task. Okay, for example, okay, say like if you have a model that that can classify like different objects, okay, then you can transfer learning that model, because that model, okay, if I draw it, so this is the model. This is the model that classify, okay, different object. For example, okay, like a person from, I mean, you can classify. It's a person. It's a car. It's a cat. Many different type of objects. Okay, then obviously the lower features, the lower layers will deal with features that are more, more simple, right? Maybe like a line orientation, as I said. This is maybe the shape and so on, and eventually it is able to detect like, okay, this is like maybe like a human or like a car at a higher layer, right? So transfer learning, what transfer learning is, the basic idea is you just copy this model and you keep the lower part of the model intact. So you copy the lower part of the model. So this part is almost identical to the previous one. Why? Because this, say like now you want to, this one is to classify different objects. This one maybe you just want to identify, maybe just identify like a different type of car. Different type of cars. Okay, so the lower layers is already able to distinguish, okay, it is car or something else, right? From this model, right? So you can copy the lower layers to here. But obviously, we are not able to identify, oh, this is SUV, or it's a sedan, okay, or like a sports car, So we need, you may need to add a few more layers. So these are the new layers. These are the new layers. New layers. Okay, so you do need to train these few new layers. Okay, but because you only need to train, for the whole model, okay, because you copy the lower part from this model, so all these layers, in addition, their weights remains. You can consider they are already trained. Okay, you only need to train these few layers, these few new layers, to be able to classify like a different type of cars. So what should I say, like, you don't need so many training instances. The training set can be much smaller, okay, and the training process can be much shorter. Okay, in fact, okay, nowadays, okay, when you want to train a CNN model to recognize to do something for you, okay, nobody train a model from scratch nowadays. Everybody do transfer learning. Okay, everybody do transfer learning. You seldom see, that you need to train the whole CNN model from scratch, because, as I said, if you want to do that, then you need a big training set, and it takes long time to train a deep neural network, okay, from scratch. But now, since transfer learning, you only need to train maybe 2-3 layers at most, then the training process is much, much shorter. Okay? So that's the idea of transfer learning, which has been used widely nowadays. Okay? We are going to talk about transfer learning, use an example to talk about transfer learning. Not right now, but in the next chapter when we talk about CNN. Okay? As for summary, of number of layers, okay, so for many problems you can start with just 1 or 2 hidden layers. So for example, like you can reach 97% accuracy on MNST data set. Okay, use just 1 hidden layer. Okay, and 98% accuracy using 2 hidden layers with the same total number of neurons. So with about the same amount of training time. So you can see, the deeper network give you a little bit higher accuracy. I mean, not by a lot, okay? I mean, the improvement is 1%, but of course this 1% is very nice. But, that's probably because like the problem itself is simple. But the idea is that you don't want to start from a lot of layers. Okay, for more complicated problem, you can ramp up number of hidden layers until you start overfitting the training set. So you can try to increase the layer, okay, until you get you have an overfitting problem. So very complicated task, okay, such as image classification, speech recognition, typically require network with dozens of layers or even hundreds of layers, okay, as we will talk about like in the CNN chapter, okay. So, but normally we don't, it's not fully connected. It's not real MLP, because MLP use dense layer that we have like a fully connection like between the consecutive layers. But in CNN, it is not like that. Okay, so you really have to train such network from scratch, as I said. Okay, we normally use transfer learning. Okay. As for number of neurons, okay, you can, for example, like for the input layer, it normally depends on your input set. Okay, if you have, how many features you have. Okay. Pretty much determine like a number of neurons in the input layer. Okay, for example, for the MNST, okay, it's the input layer is 28 by 28, 784, because that's the number of pixels, right? Okay, for the hidden layers, the number of neurons. Okay, basically like it doesn't tell you exactly what number of neurons to use, but it tells you, okay, normally you are going to form a pyramid with fewer and fewer neurons at each layer. So it's actually going to be something like where's so it's something like this. So the higher layer that has like fewer neurons. The lower layer has more neurons. Okay, this is consistent with the concept I just mentioned, because the lower layer, remember, lower layer deal with like a more fundamental features, right? More simple features, and you could have many simple features. But for complicated, for more abstract features, for example, the top ones, maybe it's already very close to like or maybe it's a human or dog or something, So the top ones, okay, for the abstract features, you don't have that many abstract features. But for the lower layer, even like the orientation, different orientation of the lines could be different features. Okay, so we have more it's suggested that we have more neuron at the bottom of the model. However, okay, so this example is like we use like, first layer we use 300 neuron, second layer 200, third layer 100. So this is consistent with the pyramid idea that we just talked about. But the newer idea is that, okay, it doesn't matter. We can use the same number of neurons for all the layers. Okay, so which one is the better? It's really hard to say. Okay, it's really hard to say. I mean, because this one, okay, if you use like a different number of neurons per layer, that means for, you need to have, you need to consider, okay, how many neurons we want to use here? How many neurons you want to use here? So you have like a more number of hyperparameters to decide, right? Because each layer you have a different number of neurons. So you have more, each layer you have one additional hyperparameter, which is number of neurons in that layer. Okay. So too many hyperparameters may also be difficult, especially when you consider you want to do like a hyperparameter, combination search, right? So some people nowadays, they suggest, oh, we just use the same number of neurons for every layer. Okay, the reason, the benefit of doing that is that, okay, now if you do that, then we only have one hyperparameter to decide, which is the number of neurons for all layers, right? So which one is better? As I say, it's hard to say. So, okay, recently there's like another idea, okay, called stretch pants approach. I mean, what is this? Okay, it's like when you are little, okay, your parents buy clothes for you. They will buy a bigger clothes for you, right? And tell you, oh, you mean when you grow up, you mean the pants just fit just right. Maybe it doesn't fit right now, okay, but after like a couple months, okay, it fits perfectly, right? So your parents, or a lot of parents do that. I mean, take me as an example. I mean, because I have an elder brother, so I always get clothes from my elder brother. So it's a little bit too big for me, but I get used to that all the time. But okay. So what is exact stretch pants approach here? Okay, basically it's like okay, it is okay to create a large model, okay, larger model for your task. Okay, you may create like a deeper network than necessary, or more number of neurons per layer than necessary. Okay, then you may wonder, well, then isn't that we are going to have like too much freedom to the model, and which will cause like overfitting easily? Yes, that's true. But remember, we have technique to fight with overfitting. We can use regularization technique, right? We have L1, we have L2, we have like auxiliary output. We have early stop, right? We have all sorts of like a technique to fight with overfitting. So you can use a larger model and then use regularization technique to confine its flexibility, it's a freedom, so that it fits right in. Okay, so this idea is called stretch pants approach. Okay, so I think in the next chapter we are going to talk about more techniques that fight with overfitting. Right now you don't. We only talk just a few of them. You don't have a full set of techniques available for you for overfitting issue. But I will tell you. In the next chapter. Okay. And for the learning rate is also obviously a very important hyperparameter. Okay, so the optimal learning rate is about half of the maximal learning rate. But you may ask, what is the maximal learning rate, right? I mean, it seems like it doesn't say anything, right? So the maximal learning rate is the learning rate above. If you have a learning rate higher than that maximal learning rate, the training algorithm will diverge. So that's like the largest one that the model training will not diverge. So the optimal one is normally half of that. Okay, but it still takes time to search, right? It still takes time to search. So finding a good learning rate is, I mean, it's going to take time. Okay, but there are other techniques out there. Actually, you can adjust the learning rate like during training. Okay, so you can use a larger learning rate at the beginning of the training and gradually shrink learning rate when the training, converge to the optimal place. So, so this type of concept is called learning scheduling. Okay, learning rate scheduling. We are going to talk about learning rate scheduling. There are actually many learning rate scheduling out there. I mean, we are going to talk about them in the next chapter. Okay. And there are also a lot of different optimizers out there. I mean, as I said, you guys only know the gradient descent, but there are many optimizers out there. Okay, that which actually has a big influence on the model performance. Okay, so we are going to talk about that next chapter. Okay, and also the batch size. Because as I said, we normally use a mini batch, right? So how big is a batch size? Okay, so well, the batch size, okay, normally like it depends on the GPU, I mean as well. But normally we set the batch size to be 32. Okay, and there's an interesting comment from Yang LeChong. Okay, you guys know Yang LeChong, right? We talked about Yang LeChong. This guy, I mean, at the beginning of the class. I mean, this guy is now like the Facebook AI lab director. Okay, and he's a professor at NYU. Okay, New York University, and this guy is really good. Okay. As we will talk about in next chapter, he is really a pioneer, okay, of this deep learning. So in early 2018, okay, Yang LeChong comment that friends don't let friends use mini batch larger than 32. So he back up the idea, okay, that mini batch, should be smaller or equal to 32. Okay. So I mean, there's a because he cited a paper, okay, 2018 paper from this bunch of people, and this is also there are also some debates for this. Okay, some people prefer to use like it was possible to use a very large batch size up to like 8K. Using various techniques, and such as warm up, the learning rate, and so on, and etc. But in general, okay, let me put it this way, okay, Yang LeChong's suggestion, okay, work most of the time, okay, at least in a simple setting, Yang LeChong's suggestion is true, okay. So, and also I want to emphasize that. If you change any setting, such as batch size, such as like the network architecture, for example, like adding more neuron or change like a number of layers, remember you need to tune your learning rate again. Okay, this is like something you need to remember. And activation function, number of iterations for activation function, okay, right now, you guys have only seen like a ReRU, right? And sigmoid maybe, okay. But later on, we are going to talk about more different activation functions out there, okay, in the next chapter, okay. And for the number of iterations, if you use early stoppings, then the number of iteration is not an issue, okay. You don't need to worry about that. You can set it to be a very large number, and set an early stopping to let it like a training stop, like when the model is already converged. Okay, so so this is not the issue. Okay, so this is like the conclusion. So they are, for more best training practice regarding tuning neural network hyperparameters. So they are like a paper from Leslie Smith that you can check out. Okay. So I think like they are also like we can customize models using TensorFlow low-level API and how to load and pre-process data efficiently using the data API. Unfortunately, we are going to skip that chapter. Okay, we don't have time to go over every chapter in the textbook. We just simply don't have that much time. But that chapter, I think like the low-level API and like the API for like data preprocessing. I think I think it's a chapter 10 or 12. I forgot. But I think you guys can check it out yourself. Okay. Let me put it this way: without that chapter, you can still take the other chapters, that we cover like without any problem. Okay, so that's about it for this chapter. So that's how much do we try to? Okay, we still have like 15 minutes. What happens? How come it's丘皮啊，你可以帮忙调一下吗？怎么又变这样子？因为我没有遥控器。遥控器。你这个可以帮忙。这样。很奇怪，就是怎么变得这么？是变太大吗？还是？This is much better. Okay, 这样可以，谢谢。Okay. So, okay, in the previous chapter, okay, chapter 10, okay. By the way, we just finished chapter 10, okay, and now we are on chapter 11. In chapter 11, okay. So chapter 11 talked about like how to train the techniques on how to train the neural networks. Okay, so so we although we try to train our neural network in the previous chapter, okay, but it's a very shallow DNN with only 2 hidden layers. So when you have a complex problem and if you want to create like a more complex model, and you may have like 10 layers, each containing hundreds of neurons, and you will find that simply using simply using the fit to train the model a lot of time doesn't work. Okay, it doesn't converge. Okay, it will not be a walk in the park. It's not that easy. Okay, so what are the problems? What caused the training to be difficult? Okay, the first one, okay, you would face the tricky vanishing gradient problem, or on the opposite, exploding gradient problem, okay, which will affect the deep neural network and make the low layers very hard to train. Okay, so this is like you know, the first issue. The second issue is you may not have enough training data. Okay, you may only have like a limited amount of training data, but you for a very complicated task. So what do?